think about the world right now. It feels a bit like things are changing fast. But imagine Earth, not just a few years or even centuries ago, but millions of years back. Deep in our planet's past, life wasn't just evolving slowly. It was getting absolutely hammered again and again. Scientists talk about the big five mass extinctions. These are the ones everyone knows. The one that took out the dinosaurs, for example. But what if I told you that was just scratching the surface? What if there were many, many more? Maybe as many as 17 or even more massive die-offs that reshaped life on Earth, or events so big they almost wiped the slate clean. We are talking about times when 70%, 80%, even 90% of all species vanished, just gone. And the scariest part? For many of these, we still don't really know why. We have theories, sure. Big ideas about volcanoes, asteroids, ice ages, or even something from space we can barely imagine. But the exact answers, the real mechanisms, they often slip through our fingers. Think about the sheer scale. Millions of years go by, life gets comfortable, branches out, fills every niche. Then, seemingly out of nowhere, something utterly catastrophic happens. Not a gradual decline, but a sudden violent upheaval. Entire families of creatures, whole ecosystems just blink out of existence. It's like a cosmic reset button was pushed. And this didn't happen once or twice. It happened over and over. Each time, Earth started fresh, life found new ways to survive, but the scars remained. The fossil record is full of these gaps, these sudden endings that mark the close of an era. This isn't just academic curiosity. Understanding these ancient catastrophes tells us something profound about Earth's resilience and its fragility. It tells us about how easily life can be disrupted. It also makes you wonder about our own time. Are we living through another one right now? What can these past mysteries teach us about the future of life on this planet, including our own? It's a heavy thought, but the history of Earth is a wild, often terrifying story. And the chapters about mass extinctions are some of the most dramatic pages. Number 17, what does it mean when the Earth itself starts to break apart? Let's talk about the supercontinent cycle. It sounds like something from a fantasy novel, but it's very real. And the Earth's continents are not fixed. They drift, collide, and break apart over hundreds of millions of years. This process is called plate tectonics, and it's fundamental to our planet. But these massive changes are not always smooth. They can cause incredible stress on the planet. And sometimes this stress leads to catastrophe. Imagine a continent, a massive landmass starting to rip apart. This rifting doesn't just happen over a few years. It takes tens of millions of years. But when it does, it's not a quiet process. It's often associated with massive outpourings of lava. These are called large igneous provinces, or LIPs. One of the most famous and devastating examples is the Central Atlantic Magmatic Province, or CAMP. This wasn't just a few volcanoes. This was an area covering millions of square kilometers, stretching from modern-day North America to South America, Europe, and Africa. The CAMP event happened around 201 million years ago, right at the boundary between the Triassic and Jurassic periods. And guess what? This timing aligns almost perfectly with the end Triassic extinction event. Geologists like Paul Olson from Columbia University have spent decades studying this. They look at rock layers, magnetostratigraphy, and fossil records. The evidence shows an abrupt change at this time. The CAMP eruptions spewed colossal amounts of carbon dioxide and sulfur dioxide into the atmosphere. This wasn't just local pollution, this was a global climate disruption on an unimaginable scale. The carbon dioxide caused rapid global warming. Ocean temperatures rose significantly. The sulfur dioxide, in contrast, caused short-term cooling, but then the CO2 effect dominated. The warming oceans, especially at lower depths, lost oxygen. This led to widespread anoxia-dead zones where most marine life couldn't survive. Dr. Stephen Hesselbo from the University of Oxford and his team have found evidence for this rapid warming and ocean acidification. They studied isotopes in ancient sediments, like carbon isotopes, which act as fingerprints for massive carbon releases. The signature is clear. On land, ecosystems collapsed. Many large amphibians and reptiles like phytosaurs vanished. It paved the way for the dinosaurs to become the dominant land animals in the Jurassic period. Before this, dinosaurs were just one of many groups. After the end Triassic extinction, they took over. It was a complete reshuffling of life, but even with the compelling evidence for camp, there are still unknowns. Was camp the only trigger? What about the actual timing of the eruptions versus the extinction pulses? Were there multiple pulses of volcanism and multiple extinction events within a relatively short geological window? The exact link is still being refined. So, here's what we still don't know. How quickly did the climate change happen? Was it truly instantaneous on a geological scale, or did it unfold over thousands of years? Could there have been other, smaller events that contributed to the stress on ecosystems leading up to the main eruption? And how did some species survive while others, seemingly similar, perished? For number 16, what happens when the oceans run out of breath? The world's oceans are vast, deep, and full of life. They seem endless, but they are also fragile. And sometimes, in Earth's deep past, these massive bodies of water suffered from a terrible sickness. They stopped breathing. This is called ocean anoxia, or oxygen depletion. It's when the oxygen levels in the water drop so low that most complex life cannot survive. And this has been a major player in several mass extinctions. Think about what happens when too much nutrient runoff goes into a lake today. Algae bloom, then die, sink, and their decomposition consumes oxygen, creating dead zones. Now imagine that on a global scale. In the past, massive volcanic eruptions, like those from large igneous provinces, often pumped huge amounts of carbon dioxide into the atmosphere. This led to global warming, which in turn warmed the oceans. Warmer water holds less dissolved oxygen. Plus, warmer water expands, changing ocean circulation patterns. It can slow down the deep ocean currents that typically bring oxygen-rich water from the surface to the bottom. One prime example of this ocean anoxia as a killer is linked to the late Devonian extinction around 372 million years ago. This wasn't one single event, but a series of pulses, the most famous being the Frasnian-Famennian event, or Kellwasser event. Marine invertebrates like brachiopods, ammonoids, and corals were hit especially hard. They lived in shallow, warm seas, and their fossils show a dramatic decline. Geologists like George R. McGee Jr. from Rutgers University have studied these ancient anoxic events for decades. His work highlights the prevalence of black shales from this period. Black shales form in oxygen-starved waters where organic matter doesn't fully decompose. They are like a dark testament to dead oceans. Another major event where ocean anoxia is a key suspect is the end Permian extinction, often called the Great Dying. This was the biggest extinction event in Earth's history, about 252 million years ago. We will talk more about the Permian in detail later, but one of the main kill mechanisms alongside massive volcanism was extreme ocean anoxia. The Siberian Traps eruptions released so much CO2 that global temperatures soared. The oceans became hot and stagnant. Researchers like Professor Jonathan Payne from Stanford University have presented compelling evidence for widespread anoxia and even eosinia, where water becomes rich in hydrogen sulfide, which is toxic. This wasn't just the deep ocean, it affected shallower waters too. The mechanism is complex. Warming can lead to increased nutrient runoff from land, further fueling algal blooms and subsequent oxygen consumption. It creates a positive feedback loop of destruction. Once the deep ocean becomes anoxic, it can take millions of years for it to recover. And during that time, life struggles to adapt or simply dies out. But despite the strong evidence, it's not a simple story. Was anoxia the primary driver or a symptom of a larger problem like massive volcanism? How exactly did the anoxia spread so widely and quickly? So, here's what we still don't know. What were the exact tipping points that pushed the oceans into anoxia? How quickly did this process occur globally, or did it spread from specific regions? Were there certain trace elements or chemical changes in the anoxic waters that made them even more toxic than just a lack of oxygen? Number 15, could explosions in space reach out and kill life on Earth? We often look down at Earth for answers about extinctions, volcanic eruptions, ice ages, continental shifts. But what if the danger came from far, far away? What if something incredibly powerful, something cosmic, reached out across space and struck our planet, causing a mass extinction? It sounds like science fiction, but it's a serious hypothesis for at least one major extinction event. Imagine a star, far away, much larger than our sun, running out of fuel. It collapses, then explodes in a flash of unimaginable energy. This is a supernova, or even more violently, a hypernova, which can also produce a gamma-ray burst GRB. Gamma-ray bursts are the most powerful explosions in the universe. They release more energy in a few seconds than our sun will in its entire 10 billion year lifespan. And if one of these bursts hit Earth directly, the consequences would be catastrophic. This isn't just idle speculation. Scientists like Brian Thomas, formerly at the University of Kansas and now at Washburn University, have done detailed calculations on this. A gamma-ray burst striking Earth would first rip apart the ozone layer. This protective layer shields us from harmful ultraviolet UV radiation from the sun. Without it, life on the surface, especially small organisms and plants, would be severely exposed to deadly UV radiation. This could lead to widespread mutations and collapses in food chains, but it gets worse. The bursts would also ionize nitrogen and oxygen in the atmosphere, creating nitrogen oxides. These molecules would cause global cooling by blocking sunlight. They would also create acid rain, making surface waters and soil toxic. This combination of ozone depletion, global cooling, and acid rain would be a triple whammy for life. The leading candidate for a gamma-ray burst extinction is the end Ordovician event, around 443 million years ago. This was one of the big five extinctions. It was very complex, involving a rapid ice age and massive sea level changes. But the GRB hypothesis offers an additional or even initiating trigger. The Ordovician oceans were teeming with diverse marine invertebrates like trilobites, brachiopods, and corals. Many of these lived in shallow, sunlit waters, making them particularly vulnerable to UV radiation. The GRB hypothesis explains the sudden onset of the ice age too. Nitrogen oxides could seed cloud formation, reflecting more sunlight back into space, kicking off a rapid cooling trend. It also explains why the extinction hit marine life so hard, especially those near the surface. There's no direct smoking gun, like an impact crater for an asteroid, but the pattern of extinction, the suddenness, and the lack of other immediate large-scale terrestrial triggers like massive volcanism make the GRB an intriguing idea. It's a reminder that Earth is not isolated in the cosmos. But the question remains, how likely is it that a GRB actually hit Earth at that specific time? We can't see ancient GRBs. And what about the evidence for massive glaciation that is so central to the end Ordovician event? So here's what we still don't know. How close would a GRB need to be to cause such devastation, and how often do such events occur in our galaxy? Is there any unique geological or geochemical signature that we could find in Ordovician rocks that would confirm a GRB strike? Could a GRB only be one part of a cascade of events where it triggered the glaciation, which then caused the major extinctions? Number 14, what role did Earth's magnetic shield play in protecting life? Our planet has a powerful, invisible shield around it. This is the Earth's magnetic field. It's generated by the molten iron core deep inside our planet, which acts like a giant dynamo. This magnetic field protects us from harmful cosmic radiation and solar winds. Without it, our atmosphere would likely be stripped away over time, much like what happened to Mars. But this shield isn't constant, it fluctuates, and sometimes, it can get very weak or even flip directions entirely. This is called a geomagnetic reversal. When the magnetic field weakens or reverses, it's not like the shield disappears entirely, but it becomes much less effective. During these periods, cosmic rays and charged particles from the sun can reach closer to Earth's surface. This can have several consequences. Increased radiation exposure at higher altitudes could affect airborne life forms. But more importantly, it could lead to changes in our atmosphere and climate. One hypothesis links geomagnetic reversals or periods of extremely low magnetic field strength to extinction events. The idea is that increased cosmic radiation could ionize the atmosphere, leading to changes in cloud formation, potentially altering weather patterns and temperatures. Or, the increased radiation could damage DNA, leading to higher mutation rates and potentially stressing ecosystems. We know that geomagnetic reversals have happened many times in Earth history. The last full reversal was about 780,000 years ago, but the field strength has been dropping quite rapidly in recent times. Scientists like Professor Joseph Kirschvink at Caltech have explored the idea that these reversals could be linked to changes in biodiversity. They studied paleomagnetism, completed the record of Earth's ancient magnetic field preserved in rocks. While a direct single cause link between a geomagnetic reversal and a mass extinction is hard to prove, it could be a contributing factor. Imagine an ecosystem already stressed by climate change or volcanism. Then, the magnetic shield weakens, allowing more radiation to hit. This could be the final straw for many species. It's an environmental stressor that adds to other problems. For example, some researchers have looked at the possibility of a weakened magnetic field contributing to the end Devonian extinction event or other smaller biotic crises. If cosmic rays interact with the atmosphere to deplete the ozone layer, it could exacerbate the effects of other environmental stressors like warming or cooling. However, the magnetic field is just one variable in a complex system. Most large extinction events have multiple, very powerful geological drivers like massive volcanism or asteroid impacts. A weakened magnetic field might not be enough to cause a global catastrophe on its own, but it could certainly make things worse. So here's what we still don't know. What exact mechanism would connect a geomagnetic reversal to widespread extinctions? Is it ozone depletion, climate change, or direct radiation damage? Are there any specific extinction events where the timing aligns perfectly with a significant weakening or reversal of Earth's magnetic field, and where other major causes are absent? And how much does a temporary weakening of the magnetic field actually affect the surface of the Earth, rather than just higher altitudes? Number 13, what happens when massive asteroids keep hitting the Earth? Everyone knows about the asteroid that wiped out the dinosaurs. It's the most famous extinction event. But what if asteroid impacts weren't just a one-off thing? What if Earth has been bombarded by many large objects throughout its history, and some of those impacts caused other, less famous, but still devastating mass extinctions? The evidence for the dinosaur killer, the Chicxulub impactor, is overwhelming. Walter Alvarez, a geologist, and his father, Luis Alvarez, a Nobel Prize-winning physicist, first proposed the idea in 1980. They found a thin layer of iridium, a metal rare on Earth, but common in asteroids, so at the KPG boundary, Cretaceous-Paleogen, formerly KT boundary. Then came the discovery of the Chicxulub crater in Mexico, about 180 kilometers wide, perfectly dated to 66 million years ago. The impact would have caused massive tsunamis, wildfires, and a global dust cloud that blocked sunlight, leading to an impact winter. Then, after the dust settled, a greenhouse effect from released carbon dioxide. But Chicxulub isn't the only large impact Earth has experienced. The planet is covered in impact craters, though many are eroded or buried. Some researchers propose that there might have been other significant impact events linked to other extinctions. For example, some have suggested that impacts might have contributed to the end Triassic extinction, though the evidence for volcanism camp is much stronger there. There's also the idea of impact clusters. The solar system passes through regions of space with more comets or asteroids, leading to a period of increased bombardment. Could such a cluster of impacts cause multiple smaller extinctions or even contribute to a larger one? Scientists like Richard A.F. Grieve at the Earth Physics Branch in Ottawa have meticulously cataloged impact structures on Earth, showing a long history of extraterrestrial visitors. One intriguing idea is the possibility of multiple impacts around the late Devonian extinction. While ocean anoxia and climate change are strong candidates, some researchers have looked for impact evidence like microtectites, tiny glass spherules formed during impacts or shock metamorphosed minerals. However, definitive evidence for a large extinction-causing impact at the Devonian boundary is still lacking. It remains a hypothesis. The key with impacts is their suddenness and the immediate widespread devastation. Unlike volcanic eruptions that can unfold over millions of years, an impact event is almost instantaneous. It sends shockwaves through the planet's systems, and the after effects, dust, acid rain, climate disruption, can linger for years or decades, pushing ecosystems past their breaking point. But the challenge is always finding the crater or the specific geochemical signatures. Erosion and plate tectonics are very good at erasing ancient impact scars. So here's what we still don't know. How many other large impact events have there been in Earth's history that could have caused mass extinctions? Are there impact craters hidden deep beneath the ocean or buried under sediments that we haven't found yet? Could smaller multiple impacts rather than one giant one have the same devastating effect? Is number 12, why did a sudden ice age destroy so much life in the Ordovician? The end Ordovician extinction is often listed as one of the big five. It happened about 443 million years ago. What's striking about this event is that it's tightly linked to a rapid and severe ice age. Imagine a world that was largely ice-free, then suddenly Glaciers started to spread, sea levels dropped dramatically, and global temperatures plummeted. This was a massive shock to life on Earth. During the Ordovician period, most life was in the oceans. Trilobites, brachiopods, corals, graptolites, and early jawless fish thrived in warm, shallow seas. The continents were arranged differently, with a large landmass called Gondwana situated over the South Pole. This positioning set the stage for the Ice Age. The trigger for this sudden cooling is still debated. Some theories point to the rise of the first complex land plants. As these plants colonized land, they would have weathered rocks more efficiently, drawing down carbon dioxide from the atmosphere. A decrease in atmospheric CO2 would have led to a drop in global temperatures. For scientists like Timothy Lenton from the University of Exeter have explored the role of biological evolution in triggering such climate shifts. The expansion of plant life, even simple ones, could have significantly altered the global carbon cycle. Once the ice sheets formed, they reflected more sunlight back into space, creating a positive feedback loop that accelerated cooling. As ice grew, global sea levels dropped by as much as 100 meters. This was devastating for marine life, especially those living in shallow continental shelf environments. Their habitats simply vanished or became too cold. Entire ecosystems were disrupted. The extinction happened in two main pulses. The first pulse coincided with the onset of glaciation and the drop in sea level. The marine organisms that were sensitive to temperature changes and loss of habitat were hit hardest. The second pulse occurred when the glaciers retreated and sea levels rose again. This might seem counterintuitive, but the rapid warming and changes in ocean chemistry, including anoxia, could have caused further extinctions. This illustrates how complex and multifaceted mass extinctions can be. The end Ordovician extinction wiped out about 85% of all marine species, massive pruning of the tree of life. Yet, despite the clear evidence for glaciation, the ultimate trigger remains somewhat mysterious. Was it purely a terrestrial event linked to carbon cycles, or was there an extraterrestrial component like the gamma ray burst hypothesis we discussed earlier? So here's what we still don't know. What exactly initiated the rapid cooling that led to the glaciation? Was it truly the rise of land plants, or was there another factor at play? How quickly did the ice sheets form and melt, and how did these rapid changes cause such widespread death? And why did some groups of organisms recover relatively quickly while others were permanently lost? It's number 11. Can something as simple as mud cause global death? It seems too simple, too mundane, to be a cause of a mass extinction. But sometimes very basic geological processes, when amplified on a global scale, can have devastating consequences. And one such process is the massive erosion and deposition of sediment, or what you might simply call a lot of mud. This idea comes up when looking at some of the earlier extinction events, particularly those around the Cambrian-Ordovician boundary or even within the Cambrian period itself. The Cambrian period, starting around 541 million years ago, is famous for the Cambrian explosion, a time when most major animal groups suddenly appeared in the fossil record. Life was diversifying rapidly, but this wasn't a smooth ride. There were several Cambrian crises, or extinction events, that punctuated this period of rapid evolution. One hypothesis for some of these early crises involves large-scale changes in continental erosion and ocean chemistry. Imagine massive mountain-building events or periods of intense weathering on land. This would lead to huge amounts of sediment being washed into the oceans. This isn't just about silting up habitats, though that certainly could happen locally. The influx of sediment also brings nutrients like phosphorus and iron. While some nutrients are good for life, too much can be disastrous. An overload of nutrients can lead to massive algal blooms in the oceans. When these blooms die and sink, their decomposition consumes vast amounts of oxygen, leading to widespread ocean anoxia. We talked about anoxia before, and it's a recurrent killer in Earth's history. Excessive mud carrying excessive nutrients could indirectly create vast dead zones in the oceans. Furthermore, the physical changes themselves could be detrimental. Imagine marine environments becoming turbid, muddy, and choked with sediment. Filter feeders and bottom-dwelling organisms would struggle to breathe, feed, or even move. Changes in ocean floor conditions could alter current patterns and further disrupt ecosystems. Researchers like Shannon Peters at the University of Wisconsin, Madison have studied the patterns of sedimentation and their relationship to biodiversity through geological time. They look at the rock record to see how much sediment was being deposited and when. What they found is that periods of high sediment flux sometimes correlate with periods of biotic stress. This mechanism is often proposed for events like the Steptuan positive carbon isotope excursion SPICE event, which was associated with a minor extinction event in the late Cambrian around 497 million years ago. While not a Big Five extinction, these events show the sensitivity of early marine life to changes in its physical and chemical environment, even those driven by seemingly mundane processes like erosion. It highlights how interconnected Earth's systems are. Changes on land can profoundly affect the oceans and vice versa. It also reminds us that life in the past was often confined to specific marine habitats, making it vulnerable to even seemingly small global changes. So here's what we still don't know: how widespread and impactful were these mud-induced extinction events truly? Can we distinguish between nutrient overload leading to anoxia and purely physical effects of sedimentation? Were there other factors at play that made these marine ecosystems particularly vulnerable at these specific times? Number 10, did the Earth just shake it off by itself? We often look for external causes for extinctions, asteroids from space, volcanoes from deep Earth. But what if the planet itself just has cycles of instability that periodically lead to ecological collapses? This idea suggests that sometimes Earth's internal processes, without any specific event, might just go through periods of disruption that are enough to cause mass extinctions. One concept related to this is the idea of true polar wander. This is not the shifting of continents' plate tectonics, but rather the entire solid Earth mantle and crust rotating relative to the spin axis. Imagine Earth's entire outer shell rotating around its core. If this happens rapidly, it could cause massive changes in climate zones, ocean currents, and even tectonic stress. A region that was once near the equator could suddenly find itself at a higher latitude, experiencing a vastly different climate. Scientists like Joseph Kirschvink at Caltech have proposed that rapid true polar wander could have been a factor in some major Neoproterozoic events, leading to extreme climate fluctuations, possibly even triggering snowball Earth glaciations. While snowball Earth events like the Sturtian and Marinoan glaciations around 717 and 635 million years ago, respectively, were not mass extinctions in the traditional sense for complex animal life, they were profound reorganizations of the biosphere for early microbial life. They show how extreme planetary changes can fundamentally reset biological systems. Another related idea is that long-term, slow changes in the Earth's interior, like changes in mantle convection, could lead to periodic increases in volcanism or changes in plate tectonics that aren't necessarily catastrophic events, but more like sustained periods of elevated geological activity. This could result in prolonged periods of climate stress, increasing the background rate of extinction until a tipping point is reached. For example, there are many smaller extinction events or biotic crises throughout Earth's history that don't neatly fit into a single dramatic cause like an asteroid or a supervolcano. Some of these might be the result of a confluence of these slower internal planetary processes accumulating over time. These are often harder to pinpoint because they lack a single dramatic signature. This perspective emphasizes the inherent dynamic nature of Earth. The planet is not a static stage for life, it's an active participant, constantly changing and evolving. And sometimes these changes, even if they are normal geological processes, can be so dramatic in their scale or speed that life struggles to keep up. But it's challenging to prove a self-inflicted planetary catastrophe. The evidence for gradual internal changes is often subtle and can be hard to separate from other, more obvious external drivers. So here's what we still don't know. Are there intrinsic cycles of planetary instability that regularly push ecosystems to the brink? Can we differentiate between an extinction caused by a single event versus one resulting from a long-term accumulation of planetary stressors? And how might these slower intrinsic changes interact with faster, more dramatic events to create a larger extinction pulse? Number 9, what happened when ancient plants got too good at their job? We often think of plants as benevolent life givers, producing oxygen and food. But in Earth's deep past, the evolution of certain plants and their subsequent ecological success might have triggered some significant extinction events. It's a paradox life evolving to thrive, but in doing so, accidentally causing a major die-off. Let's go back to the Devonian period, around 419 to 359 million years ago. This was a time of massive changes on land. Early vascular plants, with their roots, stems, and leaves, started to colonize the continents in a big way. Trees, like Archaeopteryx, formed the first forests. This was a revolutionary development, but it had profound consequences for the planet. Like, as these plants spread, they began to weather rocks much more efficiently than their microbial predecessors. Roots physically break up rocks, and the chemical processes associated with plant growth accelerate chemical weathering. This increased weathering drew down massive amounts of carbon dioxide from the atmosphere. Remember, CO2 is a greenhouse gas. A significant reduction in atmospheric CO2 would lead to global cooling. This cooling is thought to be a major factor in the late Devonian extinction, particularly the Frasnian-Flaminian event around 372 million years ago. Scientists like William F. Rudiman have extensively studied the coevolution of climate and life, including the impact of plants on atmospheric CO2. The hypothesis is that the rapid expansion of forests effectively sucked CO2 out of the air, causing a rapid transition from a warm greenhouse climate to a colder icehouse climate. The cooling would have been devastating for many warm adapted marine species, which were still the dominant form of complex life. But the impact of plants wasn't just about CO2. Their roots stabilized soils, changed nutrient cycles, and increased runoff of nutrients into the oceans. This increased nutrient runoff, particularly phosphorus, into the shallow marine environments could have led to massive algal blooms. When these blooms died, their decomposition consumed huge amounts of oxygen, creating widespread ocean anoxia or dead zones. We've talked about anoxia as a killer before, and here it's linked to the success of plant life. So, the very success of plants in colonizing land created a double whammy: global cooling and widespread ocean anoxia. This complex interaction between land-based ecological innovation and global biogeochemical cycles shows how interconnected Earth's systems are. It's a powerful example of how life itself, through its evolution, can dramatically alter the planet's environment, sometimes with devastating consequences for other life forms. But the exact timing and magnitude of these plant-driven changes are still debated. How quickly did these changes happen to cause such a rapid extinction? So here's what we still don't know. What were the exact biological and geological feedbacks that amplified the plant-driven cooling and anoxia? Did other factors coincide with this plant expansion to push life over the edge? And how quickly can an evolving biosphere, even with good intentions, drive the planet to an extreme state? Number 8. What does it mean when the Earth burps out toxic gas from its oceans? We've talked about oceans running out of oxygen and anoxia, but what if the oceans didn't just become oxygen-starved, but actively started producing and releasing a highly toxic gas? This is the hypothesis of oceanic eusemia, where deep ocean waters become not just anoxic, but also rich in hydrogen sulfide H2S. This gas smells like rotten eggs and is extremely poisonous to most complex life. Imagine vast swaths of the ocean, especially the deep parts, becoming saturated with this toxic gas. It's generated by certain anaerobic bacteria that thrive in oxygen-free environments when there's also a lot of organic matter sinking from above. Under extreme conditions, this toxic H2S-rich water could rise to the surface. And if it reached the surface, it could be released into the atmosphere. A release of hydrogen sulfide into the atmosphere would be catastrophic. What H2S is a potent greenhouse gas, meaning it would contribute to global warming. But more importantly, it's directly toxic. Even small concentrations can be lethal. If enough of it got into the atmosphere, it could poison land animals and plants directly. It would also destroy the ozone layer, exposing life to harmful UV radiation, just like a gamma ray burst. This scenario is a leading candidate for one of the main kill mechanisms during the end Permian extinction, the Great Dying, around 252 million years ago. We know this was the biggest extinction event ever. Up to 90% of all marine species and 70% of all land vertebrates went extinct. The scale is almost unimaginable. Researchers like Daniel Rothman from MIT and Lee Kump from Penn State have been instrumental in developing and researching this Unexplained ocean hypothesis. They look for specific chemical signatures in ancient rocks, like sulfur isotopes, which can indicate the presence of hydrogen sulfide in the oceans. The evidence from the Permian-Triassic boundary rocks points strongly to widespread anoxia and eusenia. The ultimate trigger for this oceanic poisoning is still thought to be the massive volcanic eruptions of the Siberian Traps. These eruptions released immense amounts of carbon dioxide, leading to rapid global warming. The warming in turn caused the oceans to dioxygenate and stagnate. This created the perfect conditions for the hydrogen sulfide producing bacteria to flourish. It was a chain reaction. Volcanism led to warming. Warming led to anoxia. Anoxia led to Eucinia, and Eucinia led to mass death. This scenario paints a truly terrifying picture of planetary collapse. Not only were land and sea getting too hot, but the very air and water were becoming poisoned. It's a stark reminder of how interconnected Earth's systems are, and how a cascade of seemingly unrelated events can lead to an apocalyptic outcome. But exactly how much H2S was released, and for how long, is still difficult to quantify. And what about the other kill mechanisms operating at the same time? So here's what we still don't know. How widespread and severe was the release of hydrogen sulfide from the oceans into the atmosphere? Was it enough to cause mass extinctions on land, or was its primary impact confined to marine environments? And how quickly could the Earth's oceans transition from healthy to deeply eugenic and back again? Number 7. Could a single, massive volcanic eruption change everything? When we talk about volcanoes, we usually think of Mount Vesuvius or Krakatoa. Big eruptions, yes, but local in scale. Now, imagine something a million times bigger. Imagine volcanic eruptions that don't just last a few days or weeks, but millions of years. These are called large igneous provinces, LIPs, and they are characterized by the outpouring of vast quantities of lava and gases over enormous areas. And they are strongly linked to some of Earth's most devastating mass extinctions. The most infamous LIP is the Siberian Traps. This immense volcanic event occurred around 252 million years ago, right at the boundary between the Permian and Triassic periods. It covered an area larger than Western Europe. For roughly 1 to 2 million years, flood basalts poured out, layer after layer, creating a vast plateau of volcanic rock. Geologists like Paul Wignall from the University of Leeds have dedicated their careers to understanding this link. They analyze the geochemistry of the rocks, the timing of the eruptions, and the environmental impact. The gases released by the Siberian Traps were the real killers. Not just ash, but colossal amounts of carbon dioxide CO2, methane CH4, and sulfur dioxide SO2. CO2 and CH4 are potent greenhouse gases. Their release led to rapid and extreme global warming. Estimates suggest global temperatures could have risen by as much as 10 degrees Celsius. This was a super greenhouse event, unprecedented in its speed and magnitude. SO2 causes short-term cooling by forming aerosols that reflect sunlight, but over the long term it creates acid rain, which devastates terrestrial ecosystems and acidifies oceans. The warming and ocean acidification caused widespread ocean anoxia and Eucinia, as we discussed. Life simply couldn't cope with the combined stresses. On land, the forests were ravaged by acid rain and wildfires, and temperatures soared. This explains why the end Permian extinction, or the Great Dying, wiped out 90% of marine species and 70% of land vertebrates. It was a complete planetary collapse. Another example of a LIP linked to extinction is the Central Atlantic Magmatic Province Camp, which we discussed with the end Triassic extinction around 201 million years ago. While smaller than the Siberian Traps, it still covered a huge area and released enough CO2 and other gases to trigger significant global warming, ocean acidification, and anoxia, leading to the collapse of many ecosystems and paving the way for the dinosaurs to dominate. There are many other LIPs throughout Earth's history. The Deccan Traps in India erupted around the same time as the Chicxulub asteroid impact 66 million years ago, leading some scientists to debate its role in the end Cretaceous extinction. Some argue it was already stressing ecosystems, making them more vulnerable to the asteroid. Others believe it was merely coincidental. The sheer scale of these volcanic events is hard to grasp. They represent a fundamental disruption of Earth's carbon cycle and climate systems. But even with strong correlations, proving direct causation is complex. What specific aspects of the eruptions were the most lethal? So, here's what we still don't know. How quickly did the bulk of the gases from the Siberian Traps and other LIPs enter the atmosphere? Were there distinct pulses of volcanism that correlate with extinction events? And were some of these LIPs triggered by asteroid impacts on the opposite side of the Earth, creating an even more complex extinction scenario? Number 6, how did tiny life forms cause such big problems? When we think about mass extinctions, our minds often go to big events, volcanoes, asteroids, ice ages. But sometimes, the biggest threats come from the smallest organisms. Microbes, bacteria, and archaea are the silent drivers of many of Earth's most fundamental biogeochemical cycles. And when these tiny life forms get out of whack, they can cause planetary scale destruction. We touched on this with ocean anoxia and oozemia. Those toxic conditions are often caused by the proliferation of specific types of anaerobic bacteria. For example, the sulfate reducing bacteria that produce hydrogen sulfide in anoxic environments. These organisms are part of the normal ecosystem, but when conditions become extreme and like very warm, oxygen-poor oceans with lots of dead organic matter, they can multiply out of control and completely alter the chemistry of the entire ocean. Another way microbes can cause trouble is through massive methane release. Methane CH4 is a super potent greenhouse gas, much stronger than CO2 over shorter timescales. A lot of methane is stored in methane clathrates or methane hydrates, ice-like structures found in cold ocean sediments under high pressure. These clathrates are like frozen methane bombs. If ocean temperatures rise, these clathrates can become unstable. The methane escapes, bubbles up from the seafloor, and enters the atmosphere. A massive methane release from clathrates is a strong candidate for amplifying the warming during the end Permian extinction. It's also been proposed as a factor in the Paleocene-Eocene thermal maximum petum, a rapid warming event about 56 million years ago. While not a Big Five extinction, the petum saw significant extinctions in the deep ocean and major shifts in terrestrial ecosystems. The researchers like James Kennett from UC Santa Barbara have studied these past methane releases. The carbon isotopic signatures in the rocks from these events are highly suggestive of massive methane outgassing. The scary part about methane clathrates is the positive feedback loop. Global warming melts the clathrates, releasing methane. Methane then causes more warming, which melts more clathrates, and so on. It's a runaway greenhouse effect. Microbes also play a role in other ways. For example, certain types of photosynthetic bacteria can produce toxins. If these bloom in large numbers, they can poison marine food webs, or during periods of widespread deoxygenation, other microbes can produce nitrous oxide, another potent greenhouse gas and ozone-depleting substance. The point is that life itself, particularly microbial life, is not a passive bystander. It actively shapes the planet's environment. And when the planet's environment changes dramatically, it can push microbial communities into states that are highly destructive to other, larger forms of life. It's a delicate balance, but the exact triggers and scales of these microbial upheavals are tough to nail down. How much methane was truly released? So, here's what we still don't know. What were the precise conditions that led to these runaway microbial events? How quickly could the Earth's climate respond to such massive releases of methane or other microbially produced gases? And are there other undiscovered ways that microbial life has fundamentally altered the planet in ways that triggered mass extinctions? Number 5, what if life was too connected to survive a single blow? Imagine a vast web with every strand connected to every other. If you cut one strand, the web might hold. If you cut a few, it might start to fray. But if you hit a critical point, the entire thing collapses. This is what an ecosystem is like, and sometimes in Earth's history, the interconnectedness of life made it uniquely vulnerable to a single major environmental shock. This is the idea of cascading extinctions or trophic cascade collapses. Take the end Cretaceous extinction KPG event 66 million years ago. The asteroid hit, dust clouds blocked the sun, plants, the base of the food web, died off. Without plants, herbivores starved. Without herbivores, carnivores starved. It's a simple, brutal logic. The impact caused the initial damage, but the collapse of the food web amplified the death toll. This is what paleontologists like Kirk Johnson, director of the Smithsonian National Museum of Natural History, have documented in the fossil record. The speed of the collapse is evident, but this isn't just about asteroid impacts. Any major environmental stressor can trigger cascades. Consider the late Devonian extinction, around 372 million years ago. We talked about global cooling and ocean anoxia. These changes killed off many marine species directly. But the loss of keystone species organisms that have a disproportionately large effect on their environment relative to their abundance could have further destabilized ecosystems. For example, if a dominant reef-building coral or sponge species vanished, the entire reef ecosystem, which provided shelter and food for countless other creatures, would collapse. This would lead to a ripple effect of extinctions. The very specialization of life can make it vulnerable. In stable times, species evolve to fit very specific niches, relying on particular food sources, specific temperatures, or certain ocean chemistries. But when the environment changes rapidly, these specialists are often the first to go. Generalists, species that can eat a wide range of foods or tolerate a wider range of conditions, tend to fare better. Another way life's interconnectedness can lead to collapse is through the global carbon cycle itself. Life isn't just on Earth, it's an integral part of how Earth functions. For example, the massive bloom of marine algae at the Permian-Triassic boundary, fueled by nutrients from land, consumed oxygen and led to anoxia. But then these dead algae became food for the hydrogen sulfide producing bacteria, further escalating the toxicity. Here, life's reaction to stress created further stress. So the complexity and interdependence of ecosystems, while promoting biodiversity in stable times, can become a deadly weakness when the environment shifts dramatically. It's like building a complex house of cards. It can stand tall and intricate, but one hard knock can bring the whole thing down. But pinning down the exact tipping points for these cascades is difficult. Which species loss was the critical blow? So here's what we still don't know. How many individual extinction events were truly cascading collapses triggered by initial stressors? Can we identify the keystone species whose loss caused disproportionate damage in ancient ecosystems? And at what point does an ecosystem become so stressed that it's no longer resilient but brittle and prone to complete collapse? Number 4, did the sun itself flicker, causing havoc on Earth? We take the sun for granted. It's the stable, life-giving engine of our solar system. But the sun isn't perfectly constant. It goes through cycles of activity, like sunspots and solar flares. These cycles can affect Earth's climate over shorter timescales. But what if, over much longer geological timescales, the sun itself experienced more significant, sustained changes that could have impacted life on Earth and even contributed to mass extinctions? This is a more speculative idea for mass extinctions, but it's not entirely without merit. For example, the sun's luminosity has changed over its history. Early in Earth's history, the sun was fainter. This is known as the faint young sun paradox because Earth still had liquid water despite less solar output. This was likely due to a much higher concentration of greenhouse gases in the atmosphere back then. But what about more subtle, yet significant fluctuations in solar output over hundreds of millions of years? If the sun experienced extended periods of lower than normal activity, it could lead to global cooling. And conversely, higher activity could cause warming. These changes, even if small, could be amplified by Earth's own climate feedback loops. Another aspect related to the sun is its journey through the Milky Way galaxy. Our solar system orbits the galactic center, and this orbit isn't perfectly smooth. It oscillates up and down through the galactic plane. Some scientists, like Adrian Malott from the University of Kansas, have suggested that when our solar system passes through denser regions of the galaxy, it could encounter more interstellar dust and gas, or even increased cosmic ray flux. As an increase in cosmic rays reaching Earth, as we discussed with gamma ray bursts, could deplete the ozone layer and cause climate changes. It's a much slower and less dramatic effect than a GRB, but a sustained increase over millions of years could add long-term stress to life. Such a scenario might be harder to directly link to a single extinction event, but could contribute to background extinction rates or exacerbate other environmental stressors. The problem with directly linking solar fluctuations or galactic journeys to specific mass extinctions is the lack of a clear, direct geological record. We have no sunspot record from 250 million years ago. We have to infer these changes from other data. Most of the big 5 extinctions have very strong terrestrial or extraterrestrial causes, volcanism, impacts, ice ages that are much more evident in the rock record. However, it's a reminder that Earth is not an isolated system. It exists within a solar system, which exists within a galaxy. All of these external factors could have subtle or even profound influences on our planet's habitability over deep time. So, here's what we still don't know. Has the sun's output varied significantly enough over geological time to directly cause or contribute to mass extinctions? Are there periods in Earth's history where our solar system's galactic journey correlates with an increase in extinction events? And could subtle changes in solar activity act as a background noise that makes life more vulnerable to other, more dramatic extinction triggers? Number 3, why did Earth almost freeze solid, then burn up, all so quickly? The story of the end Permian extinction, the Great Dying, around 252 million years ago, is truly apocalyptic. It wasn't just one thing, it was a cascade of environmental horrors that pushed life to the absolute brink. What makes it so shocking is the speed and magnitude of these changes swinging from one extreme to another. We've touched on the Siberian Traps volcanism, the ocean anoxia, and the hydrogen sulfide release. But let's look at the sequence, the sheer whiplash the planet experienced. Before the main Permian extinction pulse, there's evidence for significant global cooling and even a lesser glaciation, particularly in Gondwana. Then, very quickly, the Siberian Traps started to erupt. The initial eruptions would have released huge amounts of sulfur dioxide, creating atmospheric aerosols that could have caused a short-term volcanic winter, making things even colder. This would have been a shock to existing ecosystems, but that cold snap would have been quickly overwhelmed by the release of massive amounts of carbon dioxide and methane from the continued eruptions. The planet swung from cold to intensely hot. Estimates suggest global temperatures rose by 8 to 10 degrees Celsius, possibly even more in some regions. This was rapid, catastrophic global warming. Researchers like Alexander Ritalak from the University of Oregon have studied fossil soils from this period, which show evidence of extreme heat and aridity on land, consistent with desertification. The warming then triggered the release of methane from clathrates, creating a positive feedback loop and amplifying the greenhouse effect. The oceans, already struggling with the warming and changing currents, became deoxygenated and then oceanic, with hydrogen sulfide bubbling up. What's particularly chilling is the timing. It's not a gradual decline. The most intense phase of extinction seems to have occurred over a period of perhaps only 60,000 years, or even less, according to high-resolution dating studies by researchers like Samuel Boring at MIT. On a geological timescale that's almost instantaneous, it means the planet's systems effectively collapsed within the blink of an eye. Imagine life struggling through an ice age, then being plunged into a super hot, acidic, toxic world. It's hard to conceive of any ecosystem surviving such a rapid and extreme environmental whiplash. This event didn't just prune the tree of life, it almost chopped it down at the trunk. The recovery period was incredibly long, lasting for many millions of years into the Triassic period. Simple, undifferentiated disaster faunas dominated the oceans for a long time before complex ecosystems re-established themselves. The Permian-Triassic boundary is the ultimate cautionary tale of planetary environmental collapse. It shows how multiple stressors can combine in a deadly synergy, and how quickly Earth can become hostile to most complex life. But even with all the evidence, the exact cascade of events and their precise timing are still being refined. Was there a single pulse that delivered the final blow? So, here's what we still don't know. What was the exact sequence of events? Cooling, warming, anoxia, oceania, and their precise timing during the end Permian extinction. Was there a tipping point beyond which the Earth systems entered a runaway feedback loop of destruction? And how did even a few species manage to survive this seemingly insurmountable planetary catastrophe? Number 2, were there more than 5 times life almost died out completely? We keep coming back to the big 5 mass extinctions, the end Ordovician, late Devonian, end Permian, end Triassic, and end Cretaceous. These are the titans, the ones where a significant chunk of life on Earth vanished. But the truth is, the line between a mass extinction and a major biotic crisis is often blurry. And depending on how you define it, there are far more than just 5 times when life took a severe hit. This is where the idea of 17 unexplained mass extinctions, or even more, comes from. Paleontologists and geologists are constantly refining our understanding of the fossil record and ancient environments. They identify periods where diversity drops significantly, or where certain groups of organisms disappear abruptly. Sometimes these are smaller in scale than the big 5, but still represent a substantial loss of biodiversity and a major reshuffling of ecosystems. For example, beyond the end Devonian event, the Devonian period itself saw several other extinction pulses, some specifically affecting certain marine groups like tabulate corals or placoderm fish. The Jurassic period had its own set of extinction pulses. The Torsion Oceanic Anoxic event, around 183 million years ago, was associated with global warming and significant losses in marine life. While not a big 5 event, it was a major crisis. It's often linked to the Karoo-Farrar Large Igneous Province. Even earlier, within the Cambrian period, there were several Cambrian extinction events that punctuated the great diversification of life. These were smaller than the big 5, but still saw significant losses of trilobite species and other early invertebrates. These often involved shifts in ocean chemistry, like anoxia or changes in calcium carbonate saturation. The Ediacaran period preceding the Cambrian also saw an extinction event around 540 million years ago, just before the Cambrian explosion. The strange soft-bodied Ediacaran biota, the earliest complex multicellular life, largely vanished. The cause is still debated, but could involve rapid changes in ocean oxygen levels or increased competition from newly evolving Cambrian animals. The point is that Earth's history is not a series of long, calm periods punctuated by 5 dramatic explosions. It's a much more dynamic and often violent story. There were many times when environmental stress, whether from volcanism, climate change, ocean chemistry shifts, or perhaps even asteroid impacts, caused a significant die-off. We just don't always understand the exact triggers or the full extent of the damage for these smaller events. Sometimes, the term mass extinction is reserved for events where more than 75% of species go extinct. But even losing 40 to 50% of species is a catastrophic event. It might not reshape the entire planet as dramatically as the Permian, but it still represents immense suffering and loss of evolutionary potential. Researchers like Michael Rampino from New York University have consistently highlighted the greater number of biotic crises beyond the Big Five. They look for patterns, astronomical cycles, and geological events that might correlate with these numerous extinction peaks. So here's what we still don't know. What is the true number of significant extinction events throughout Earth's history? If we broaden our definition beyond the Big Five, are there common underlying causes or mechanisms that link these numerous smaller extinction pulses together? And how much does the cumulative effect of many smaller extinctions compare to the impact of one Big Five event in terms of long-term evolutionary consequences? Number 1, are we living through the next unexplained mass extinction right now? This is the big, uncomfortable question. We've talked about events from millions of years ago, mysterious and ancient. But what about today? Many scientists, including numerous prominent biologists and conservationists, argue that we are currently in the midst of the 6th mass extinction event. And this one is different. It's not caused by volcanoes, asteroids, or natural ice ages. It's caused by us. The current extinction rate is estimated to be 100 to 1,000 times higher than the background extinction rate seen in the fossil record. This is a dramatic acceleration. Species are disappearing at a rate comparable to or even exceeding some of the Big Five events in Earth's deep past. The causes are well-known: habitat destruction, deforestation, pollution, overfishing, hunting, invasive species, and crucially, human-caused climate change. Think about the parallels to ancient events. We are rapidly increasing greenhouse gas concentrations in the atmosphere, leading to global warming. This is like the rapid CO2 release from the Siberian traps, but from burning fossil fuels instead of flood basalts. Our oceans are warming, losing oxygen, and becoming more acidic, a terrifying echo of the anoxic, eosinic oceans of the Permian. The absorption of excess CO2 by the oceans causes carbonic acid to form, literally dissolving the shells and skeletons of marine organisms. Researchers like Ove Hoye Goldberg from the University of Queensland have shown the devastating effects of ocean acidification and warming on coral reefs. We are dramatically altering the global nitrogen and phosphorus cycles through agriculture, leading to nutrient runoff and dead zones in coastal waters, just as ancient nutrient surges caused anoxia. We are physically altering landscapes at an unprecedented scale, destroying forests, wetlands, and other critical habitats, which is a direct mechanism of species loss. We are introducing invasive species that outcompete or prey on native species, simplifying ecosystems and making them more vulnerable. The speed of change is also alarming. The current rates of warming and ocean acidification are occurring much faster than most natural climate shifts in Earth's history, giving ecosystems and species very little time to adapt. Paleontologists like Anthony Barnosky from UC Berkeley have documented the stark comparison between current extinction rates and past events. The evidence is not in ancient rocks, but in our current biodiversity statistics, in the declining populations, and in the vanishing habitats. The label Unexplained might not seem to fit, because we know the cause of this one is human activity. But the full scope of its impact, the tipping points we might be approaching, and the exact future trajectory are still uncertain. We don't fully understand the complex feedback loops that might be unleashed. We don't know which ecosystems will be the most resilient or which will collapse completely. This current crisis also makes us look back at the unexplained ancient extinctions with new eyes. Perhaps some of those past events involved more complex biological feedbacks than we previously imagined, or were triggered by combinations of stressors that we are now inadvertently recreating. The past is not just history, it's a warning. So, here's what we still don't know. How severe will the sixth mass extinction ultimately be, and how quickly will it unfold? Are there crucial tipping points in Earth's climate and ecosystems that, once crossed, will lead to irreversible changes beyond our control? And as the dominant species on Earth, can we, and will we, change our behavior enough to avert the worst outcomes, or are we just another chapter in Earth's long, violent story of mass extinctions?